Hello and welcome. In this video, we're going to use parent functions to identify transformations and to graph transformations. So we're going to focus on if we graph a function using a table, can we identify what that transformation is from the parent function? And then we're going to move into looking at the functions themselves and identifying those transformations from the function itself. So let's go ahead and jump right in. Okay, so what we're going to focus on is identifying families of functions, describing those transformations, and graphing the parent function and their transformation. So a parent function is just the most basic form of a function, and you can see a few parent functions here. We have the quadratic parent function, f of x equals x squared, or y equals x squared. We have the square root function, g of x equals the square root of x. And we have the absolute value function, k of x equals the absolute value of x. And these are just three of many different types of parent functions. But what we want to do is start by just graphing those basic functions and identifying their domain and range. And then what we can do after that is use that parent function to identify how one function is being transformed. So hopefully you remember, and if you don't, you could always make a table. But the parent function for a quadratic, the vertex is at 0, 0, and then the next 2 points are over 1, up 1, or negative 1, 1, and positive 1, 1. And then the next 2 points, if I'm going out away from it, are at 2, 4. And then I'm connecting to make a U-shaped graph. So this function type is quadratic. So that's the basic gist of what I think of when I'm graphing a quadratic. I know that the vertex of the parent function is at 0, 0. I know that to move, I go over 1, up 1 to get to the next 2 points. And I know to get the other 2 points, I go over 2, up 4, over 2, up 4. And the reason I want you to be thinking about that idea is because if all I'm doing is moving that function down 1 or right 1 or left 1, I can use those same basic 5 points and how I'm shifting it in order to graph it without having to plug a bunch of numbers into the table. That's what we're trying to avoid here. We don't want to have to plug numbers into the table. So with a quadratic, domain is asking us what kinds of x's are we allowed to plug in. Well, I'm allowed to plug in anything. I could plug in a negative number. I could plug in a positive number. I could plug in 0. So the domain is going to be all real numbers, which is negative infinity to infinity. Because just as a reminder, when we use interval notation, we put the lowest value. We use parentheses with negative infinity and positive infinity because we only use those square brackets if we actually get to that exact value. And then it goes up forever, every possible high number of x. So we're talking about what we're allowed to plug in along the x-axis. It goes up forever to infinity. Now the range, I want you to think about the lowest possible value that we can see on our graph and the highest possible value that we can see on our graph. So the lowest possible value is right here. The graph never comes down any further. This is the lowest it ever goes. So that's the first part of my interval, and that's 0. And is the y value ever 0? Well, sure. If x is 0, then y is 0. So I use this square bracket instead of the parentheses. Then how high is my graph going? Well, it's going up forever. So it's going up towards infinity, and we always use parentheses with infinity. Okay, same idea with the square root graph. Square root. The basic graph is our perfect squares. So the square root of 0 is 0. The square root of 1 is 1. The next number that I know I can take the square root of evenly is 4, and the square root of 4 is 2. And then I can connect to make sort of like a half parabola sort of shape. When I'm talking about the domain, I'm asking myself, can I plug in all x values? And the answer for this function is no. We can't plug in negative numbers because if we took the square root of a negative number, that would be an imaginary number, and we haven't talked about that yet. The smallest number that we're allowed to plug in then is 0, and 0 is allowed to be plugged in, so it's that square bracket, and we are going to the right forever, so that's going to be infinity. So again, with our interval notation, we're looking smallest, comma, largest, whether we're talking about X or Y. The square brackets would mean that that number is included, and the parentheses would mean that that number is not included. So just as a reminder, our range is going to be exactly the same. We're never getting a negative y coming out, so the smallest y is 0, but the y's can go up forever and ever. All right, absolute value, which is really just two lines, one with a positive slope and one with a negative slope. Absolute value, everything becomes positive. So 0 stays 0, 1, 1, 2, 2. This is going to keep going, and it's going to keep going with the negative direction as well. An absolute value graph should look like a V as opposed to a quadratic graph that should look like a U. So I'm connecting here. So we should write this is absolute value, is that type of function. Now I want you to see if you can identify the domain. What is the smallest x value? What is the largest x value? So remember, smallest and largest for x is talking about left and right, and I'm going left forever, which means negative infinity is my smallest x value, and I'm going right forever, which means positive infinity is my largest x value. Now I want you to ask that same question with your range. Range is up and down. It's your y-axis. So what is the lowest that your graph ever goes, or the smallest, and what is the highest it ever goes? So the lowest it ever goes is 0, and it's going up forever. So the range is from 0 to infinity. So now that we've spent some time looking at these parent functions, let's go ahead and see if we can use those to help us identify some transformations. We're going to look at some vocabulary, and we're going to do a little bit more graphing. So let's start off with some vocabulary. Functions that belong to the same family share the same key characteristics. All parabolas have symmetry. All square root functions have values that are excluded. They share similar characteristics. The parent function, which is something I have been already using, but let's go ahead and define. The parent function is the most basic function in that family. Functions in the same family are transformations from their parent function. So if I have just taken one of those quadratics and moved it up or left or right or flipped it upside down, those are all transformations of the basic parent function. A transformation can change the shape, size, position, or orientation of a graph. A translation is a shift in the graph, whether you're moving it up, down, left, right, or a combination. A translation is the mathematical word that we use for shift. A reflection is a transformation that flips a graph over a line called the axis of symmetry. So a reflection is exactly what you think. You're flipping something or you're reflecting something over a particular line. And then the last transformation that we're going to talk about is what happens if we multiply all the y coordinates by a value, and that's called a stretch or a shrink. So if we multiply all of the y coordinates by something that's greater than 1, then we are creating a vertical stretch. If we multiply all the y values by something that is less than 1 or between 0 and 1, that's going to result in a shrink. And we'll get a more visual understanding of what that means when we start graphing these. Now, these words should sound relatively familiar from geometry, but in Algebra 2, we're going to focus not so much on shapes, such as triangles, and using these to help us identify characteristics of those shapes. We're going to be using them to describe transformations from a graph or to create transformations on a function from the parent function or from a different function. So we're going to be looking at these through a different lens in Algebra 2. So let's go ahead and look at some examples. Okay. What I want you to do before we jump into the transformation part is I actually want you to just graph the parent function. So pick maybe a lighter color and just graph the parent function for number 4, which would just be the quadratic g of x equals x squared. And I'm just picking g because this already says f, so I want to pick a different letter. And you can look back up at the top of your paper to identify that. And similarly on number 5, I want you to graph the parent function, which is just going to be the absolute value of x. So just go ahead and pause the video and recreate those parent functions on your graph first. So here I have created my parent functions on the graph. And again, for that quadratic, I start with my vertex, I go over 1 up 1 on each side, I go over 2 up 4 on each side, and then I connect. And I really want you to think through that because that's going to help you graph with something new that we're going to learn today. So we are going to take the same basic 5 values that we normally plug into a quadratic here and make a table to identify what these values are going to be. So if I plug in -2 and I square it, I get 4. If I add 1 to that, I get 5. The same thing's going to happen if I do +2. If I plug in -1 and square it, I get +1. And if I add 1, I get 2. Same thing with +1. And if I plug in 0, I get 1. So all I've done here is use this table to plug in values for this new function f. And then let's go ahead and plot those points. -2, 5, -1, 2, 0, 1, 1, 2, 2, 5. Go ahead and plot those 5 points. So something I want you to notice is that this graph has actually the same pattern as the one that I just did. The only difference is I have moved all of my points up 1. So my vertex starts at 0, 1, but then I still go over 1, up 1 to get to my next point. I still go over 2, up 4 to get to the next point. So it's the exact same shape, except it has translated up 1, right? The word for shift is translate. So transformation, it's translate up 1. How has that changed the domain? Well, I'm still allowed to plug in any x value that I want. So the domain hasn't changed at all. How has it changed the range? Well, before my lowest y value that I could see on my graph was 0, but this has shifted up 1. So the lowest y value is not 0 anymore. It's 1, and it's still going up forever. All right, we're going to use the same 5 values for our absolute value graph. Now remember, absolute value makes the number inside positive, but this negative afterwards is going to happen last according to the order of operations. So if I plug -2 in there, it's going to become +2, but then we're going to make it negative again. If I plug in -1, it's going to become positive, but then we're going to make it negative again. 0 is still 0. 1 is going to become -1. 2 is going to become -2. So go ahead and pause the video, fill in that table, and then add those values to your graph. So the big difference here is it looks like I just flipped that purple V-shaped graph for the absolute value. It looks like I just shifted it or reflected it upside down. Now it's opening downward instead of upward. So where is it? It's reflecting, and then over which axis? It looks like it's reflecting over the x-axis. Domain-wise, I'm still allowed to plug in any x value, but range-wise, it's a little different. The smallest, that's what I'm asking myself with range, the smallest it ever goes, well, it's going down forever. So the smallest it ever goes is -infinity. The highest it ever goes is right here, and that's just back to 0, and it can be 0, so I'm going to have a square bracket there. All right, let's look at 2 more examples. All right, so go ahead and graph the parent function. And what is that parent function? It is the quadratic. Go ahead and add that onto both of your graphs, 4, 6, and 7. Okay, now we're going to make our table. So I'm going to use the same 5 values. If I plug -2 in, -2 plus 1 is -1, squared is 1. If I plug -1 in, I get 0, squared is 0. If I plug 0 in, I get 1. If I plug 1 in, I get 2, squared is 4. If I plug 2 in, I get 3, squared is 9. I'm not sure that's going to fit on my graph, so I'm going to plug one more value in. I'm going to plug -3 in, since I don't want to get any bigger, and I still need 5 points on my graph. If I plug -3 in, I'm going to get -2 squared, which is 4. So let's go ahead and look at this graph. -3, +4, -2, +1, 1, -1, 0, and then coming back up. What I hope that you're noticing is we still have that same pattern. We have our vertex, and then we go over 1, up 1 to get our next point. From our vertex, over 2, up 4 to get our next point to create our U-shaped graph. That shape is the parent function shape. So notice it's not being stretched or shrunken at all. It's just shifting. And which way is it shifting? Well, it looks like it has shifted left 1. So we're going to say translate left 1. And how has this affected the domain? Well, it hasn't changed the domain at all. And in fact, it hasn't changed up and down what's happening either, so the range is still going to be the same. All right, I want you to pause the video and try and work through number 7 on your own, and then unpause the video and see how you did. So something sort of weird happened on this graph. I plugged in all my values and I got all the values I normally get because I'm making them negative and then I'm squaring it, which makes them positive. Now that negative sign indicates that I'm reflecting, but it doesn't really look like anything has changed from my parent function to my new function. That's because when we reflected over the y-axis, which just made everything land right on top of itself for this particular function. So it does look exactly like the parent function. So we've talked about reflections and we've talked about translations. Let's look and see what happens when we stretch or shrink our graph. I'm actually going to encourage you to pause the video and try and work through number 8 on your own. You might not be able to answer the transformation part yet, but you can graph the parent function, you can plug in values, you can find the domain and range, and then unpause the video and see how you did. All right, so hopefully you had some time that you did actually pause the video, or you can pause it now, to add this graph in here. And what I'm hoping you noticed is that it's like this graph got a little bit skinnier. It's like we pulled it up and down. We pulled on these ends up and down to stretch it up along the y-axis, or to stretch it vertically. So the transformation here is a vertical stretch, and we're going to say by a scale factor of 2, and that 2 is coming from here. The domain hasn't changed, and in fact, the range hasn't changed either. All that's changed is how quickly we're getting bigger numbers. I'm going to have you try number 9 on your own, but I'm going to suggest that since we're going to multiply things by 1/2, I'm going to suggest that instead of using -1 and +1, that you only use even numbers to make that a little easier. So go ahead and pause the video and work through this on your own. So those are not my straightest of lines, but that's okay. I think that you can see is that it's getting a little flatter. It's like we were pushing things along the y-axis instead of pulling them. So what's happening here is that we have a vertical shrink by a scale factor of 1/2. What you're going to notice is that these stretches and shrinks aren't really changing the domain or the range at all for these functions, because it's not changing the input and output, it's just changing how quickly or how slowly the numbers get bigger. So now that we've spent a solid amount of time looking at these from graphs, let's see if we can identify and more formalize those transformations from the functions themselves. Because I don't think that you want to have to graph a function every time you're being asked what the transformation is. All right, here we go. Something that I have learned students found helpful is having an acronym that helps you identify how you're going to describe your transformations. So when you're looking at a function, the horizontal transformations are going to happen on the inside of the function. And on top of that, they are the inverse of what you think they should be. So if you see +1, that actually means left. If you see -1, that actually means right. Vertical transformations happen on the outside, and they are what you think they should be. So they are the original thing that it looks like. What you see is what you get. So horizontal transformations are inside the function. So we're saying that means inside the thing that's being squared, inside the absolute value, inside the square root. All of those are transformations that are happening horizontally, as opposed to vertical things are happening outside of that square root, outside of the absolute value, outside of the squared signs. So just keep that in mind. HIVO, horizontal happens inside and it's the inverse of what you think it should be. Vertical happens outside and it's the original. It is what you think it should be. When you are describing multiple transformations, we're going to list the horizontal transformations first and then the vertical transformations. And we're always going to do it in that order. We're sort of just going to make a little list to go off of that. So let's look at some examples so we can really understand what we're saying here. I'm going to try and use a lot of color to make this very obvious. So here are my absolute value symbols, which means everything that's happening inside is a horizontal transformation. This plus 2 means that we are moving to the left. So the very first thing I'm going to write is that we are moving left 2. Horizontal, and actually let's say translate left 2. Let's use appropriate vocabulary here. Translate left 2. That's the only thing that's happening inside the absolute value that makes it different than the parent function that was just the absolute value of x. There are a couple of things happening vertically, and we want to work around what's happening to that absolute value. So if we were thinking about the order of operations, after we do the absolute value, the next thing we do is multiply by this -3. And there's two things that are happening there. That negative sign means that we are reflecting across the x-axis, and the 3 means that we have a vertical stretch because 3 is greater than 1 with a scale factor of 3. The last vertical thing that's happening, the very last thing we would do if we plugged a number in for x, is this -4. Vertical is outside and it is what you think it should be, so that is a translation down 4. Okay. For number 11, our parent function, again, is the absolute value function. And the first thing I want you to do is just highlight or underline or identify what the horizontal stuff that's happening is. So here's our function. Identify what's happening inside that function. So hopefully you had time to do that, and the first thing you noticed was that we have this -4. What that means is that we are translating 4, and it's the opposite of what we think, so we're translating 4 to the right. Fix my colors there. Vertically, there's two things that are happening. There's this 1/4 and this +8. What would happen to the absolute value first? We would multiply it by 1/4. So there is a vertical shrink because that 1/4 is between 0 and 1 of 1/4, and the +8, we are translating up 8. Let's look at a couple more. All right, here we go. I'm going to encourage you to pause the video, identify the parent functions, and see if you can identify those transformations, and then unpause the video and see how you did. All right, parent function here is going to be x squared. Actually, for both of these it is. Let's talk about the horizontal stuff first. The horizontal stuff is everything that's happening inside the thing that's being squared. So the first thing that's happening on 12 is that -3. What that -3 means is that we're translating 3 to the right, or translating right 3. What the +5 means is that we're translating 5 to the left. Next, we're going to look at things that are happening outside of that function. So over here, the only thing happening outside is that negative, and that negative is a reflection across the x-axis. We'll talk about if it's inside, it's the y-axis in our next video, but we did see an example like that. There's two things happening on 13. There's this 2 in front and this -1 in back. Which of them would happen first to the thing that's being squared? The 2. So that's a vertical stretch by a scale factor of 2. And then this -1 would happen last. So the last thing we're going to list is that we're translating down 1. So having those bullet points, listing them out, is really the best way for you to make sure you're hitting everything. Start with the horizontal, then work your way out based on what would happen to the function itself from the parent function. The last thing we're just going to get briefly into before we end out this lesson is what happens if we're performing a transformation on something that's not the parent function. So what happens if we're actually looking at this function and we're going to change this function to be something else? So what I want you to think about first is, again, what's different from one thing to the next? Start by listing inside, horizontal stuff first, and then work your way outside. So here's my inside function. Here's my inside function. I'm asking myself what's different. Well, the first thing that I notice is originally in the function they gave us, there was a -1, and now there's a +4. So that -1 means that we are translating to get from that -1 to the +4. So we're translating 5, right? Because to get from -1 to +4, I'm moving 5 spaces, if you think about that on the number line. But which way? I'm moving, this is becoming a plus, so the opposite of what I think it should be. It's going to be left. So this is translating 5 to the left. I'm going to work my way out now. The next thing that I notice is that this number in front wasn't here before. So that means that we have a vertical shrink with a scale factor of 1/2. And then there's one other thing that's different. Do you see it? There was originally a +2 here, and now that +2 is gone. So if I had a +2 and I'm getting rid of it, I'm subtracting 2, and subtracting 2 means that we are translating 2 down. Now this whole section here, this is really a push. If you have understood everything perfectly so far and this part is getting you a little bit more confused, don't worry, we're going to spend more time on this. But if you're following this, that means you're really understanding at a deeper level. But these last 2 examples are not the most important thing that we're learning in these notes today. I just want to make sure that you know that. I'm actually going to change one thing on this next problem because we haven't talked about horizontal shrinks yet. So let's actually move that 2 onto the outside. Sorry, I'm just editing this problem because I don't think we should talk about horizontal stretches and shrinks if we haven't talked about what they are yet. So actually here, let's just rewrite this. We're going to call this g of x equals 2 times x minus 2 quantity squared minus 4. So the first thing I want you to do is just identify the differences. So go ahead, pause the video, identify the differences. Okay, now that you've identified the differences, see if you can list out what they are. So I'm going to give you a hint. There's one horizontal thing that's happening, and there's 2 vertical things that are happening. So pause the video and see if you can work through those. All right, hopefully you paused the video and took your time. We were going from -1 to -2. So we have shifted 1 to get from -1 to -2. We have shifted 1, or translated 1 to the left. Nope, sorry, 1 to the right, opposite of what I think it should be. This 2 in front means that we have a vertical stretch with a scale factor of 2. That wasn't there before. And then we're going from +2 to -4. So we're shifting 6, right? To get from +2 to -4, we're shifting 6 to the right. So translate 6 to the right. Okay, so the key ideas in this section. We want to be able to graph a parent function quickly and then be able to graph another function using that function as our foundation, as our base. So using the parent function and how it behaves to graph a new function. The second focus in our lesson was on how to identify what a transformation is by looking at the function, and we did that using HIVO. Horizontal is our inside changes, and they are the inverse of what we think they should be. Vertical are our outside changes, and they are what we think they should be. So being able to talk about the translations, left, right, up, down, the stretches or shrinks vertically, what's happening when we reflect across the x or the y axis, being able to list those out in the correct order. So go ahead and write down any questions you have, and I look forward to supporting you on this. Thanks for listening.